Let's see, and this diagram has three perpendicular bisectors drawn in. So each of these on the diagrams on the right, I put three of them in. Three of them in for you at once. Alright, so again, perpendicular, each right angles, and the bisect part, it must go to a midpoint. That's a review one. So is angle bisector. I'm not going to spend a lot of time on this one. It's a ray, so there's a segment that divides an angle into two congruent angles. So here's my angle bisector. It's marked by having these two little arcs there. So guys, all four of these, by the way, if you put in three of these segments, so three angle bisectors, you notice how they all meet at a central point there. Okay, and this is something they used to have us do, but we no longer do it. So it used to be a standard to name these points, not anymore. But all four of these types, they're going to meet, if you put in three of that type of segment, they'll meet at a point. Oh, I know what else I want to say. Perpendicular bisector is the only one that does not have to go through the vertex of the triangle, or go through one of the vertices. I asked earlier, and that's why this is up here, when would the perpendicular bisector go through the vertex? Like, what type of triangle would it have to be? Scalene, obtuse. What type of triangle? What type of triangle would it have to be for my perpendicular bisector to go right through the vertex? Emily? Equilateral. Thank you. That one took a second. That's fine. Equilateral. If it's equilateral, okay, three sides congruent, three angles. Well, if it's equilateral, then my perpendicular bisector, in order to go right through there, the midpoint, it would actually go through the vertex as well. Maybe you're gonna say
Wouldn't
it.
it also be able to work with isosceles?
Only for so for equilateral, it would be for all three sides.
Oh, for all three.
Yeah.
Okay, that makes sense.
For all three. But you're right. If I had maybe like an isosceles triangle like this, like the perpendicular bisector for this side would be like here. That's not gonna go through the vertex.
Yeah. Okay. Makes
But
sense.
certainly for this one, it would work for that one. You would go through the vertex there. Yeah, good point, Charlie. Thank you. So the other three must go through a vertex. We did this one, right? So angle bisector. So let's go on median. I think midpoint. It's a segment whose endpoints are a vertex. There it is. Goes through a vertex, and it goes through a midpoint of the side opposite. And here's an example. There's a vertex. It goes to an opposite side. We must have this marking, otherwise we cannot assume it's going to a midpoint. So those are congruent, therefore it's a midpoint. And finally, altitude, I think height, so just height of a triangle. Now the one thing, in order for it to be the height of a triangle, it must go straight down from a vertex, so that's the top. And straight down, it's going to be at a right angle, so perpendicular. So it starts at a vertex, a segment from the vertex, and is perpendicular to the opposite side. So again, the 2, 3, and 4 of those, they have to go through a vertex. 2 of those should be new, 2 of them should be review. Any thoughts on those 4? Take 1 minute. You see 1, 2, and 3 below. I want you to label those. What do you think? Based on the markings, is it a perpendicular bisector, angle bisector, median, or altitude? It's one of the 4. You cannot write none. Okay, take 1 minute. See what you think each of those are. let's say it did. What'd you put for number one? What'd you put for number one? Okay, Madison. Altitude? I'm gonna start to write it. You guys agree?
No.
Mixture review there. I agree. I bet some of you put perpendicular bisector. That's what I found earlier. You know what? Because you see the word perpendicular and you see the right angle, so you're probably like, oh, it's perpendicular. But this one's 3 and that one's 3.2. So that right there is not a midpoint. And so if it's not a midpoint, it can't be it's not bisected. So mixed review on that one. But yes, no, Madison, good job. It is an altitude. Just height starts at a vertex, goes straight down. At a right angle. 2. Good job. Median. You guys disagree? Having fun with this. I agree. That's a midpoint because those are marked as congruent. And so yeah, it's median. Nice. And 3 to finish up. No, I'll go with Emily. Nice. Angle bisector? Yeah, nice. 3 for 3. That was good. None of my other classes were 3 for 3. So you guys. What? What? I'm not saying. That's we'll let the actions and the results speak. What questions can I answer on that? Those 4 types of segments. Sounds good. We're going to look at a few properties of these. Now the first one is more a general understanding. We're not going to prove this one. But let's look at a few properties in general. This one, some of these don't have names. This one does not. This was one I'm never going to ask you to prove. It's just conceptual. If I have a point here and I have a line here, do you think the shortest distance from the point to the line is a diagonal line?
No.
No. It would certainly be the one straight down, right? Just directly to the line. Straight down is perpendicular. So if you have a perpendicular segment, it's the shortest. So what do I say here? The perpendicular segment from a point to a line is the shortest segment. That's pretty much what that's, oh yeah, same thing too. There's a similar theorem for 3D. Corollary is just like a little theorem based off this one. It just says if we're not on 2D, if we're now in 3 dimensions, so I have a plane here, and here's my point, the shortest distance to the plane is not diagonal. The shortest distance is straight down at a right angle. So that's what it says here. The perpendicular segment from a point to a plane is also the shortest segment. Make sense overall, right? It's not something I would test you on, but it comes up in a theorem in a second, where we have to know that the perpendicular segment is the shortest. Okay, here is an OST theorem, meaning this is one they directly say to know how to prove. We're going to show that any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. If this diagram looks familiar, it's because it was, I think, number 1 from Friday. From the cutout proofs activity, it was one of those. So we actually already did it, but you didn't know what you were actually doing. You didn't know we were actually proving it. So let me explain this one, and you first need to know this important vocab word. I don't think you know this one. Equidistant. Do you think you're able to crack the code of what that one means, though?
Equal distance.
Equal distance, yes. So, I will use that from time to time. I'll say equidistant, meaning equal distance. It's just a word that kind of combines it into one. So, any point, here's what it is. This right here is a perpendicular bisector. I know that because of the right angle and these marks. So it says this. Well, do you have a segment, not like a full line going on forever? Here's a segment, AB. If I choose any single point that I want on the perpendicular bisector, suppose I choose M, then the distance from M to the endpoints A and B are the same. And hopefully that's one that you can, okay, that should make sense. If it's on a perpendicular bisector, it's straight up and down, and it went through the middle of the segment. That's why it works. Went through the middle of the segment, sure, then I go up here. I can choose at any point, so there to there, and A to B there, congruent. That segment and that segment, same length. Any point I chose on my perpendicular bisector. So we will prove this one in the practice. Again, if you're not sure, if you're struggling in the practice, it's number 1 from what we did Friday. To show that AM and BM are congruent, we just show the triangles on. So it boils down to triangle proof. You do reflexive property. You do that this is a bisector of this segment, so these are congruent. And then you do a 2-step process to say that these are, since perpendicular, these are right angles and congruent. And then the triangles will be congruent by SAS. The converse, the reverse is also true. So that says, if you're trying to decide, hey, is this a perpendicular bisector? If you know these two lengths are equal, then any point you choose, if you choose a point here and these distances are equal, then this is a perpendicular bisector. And move on to the next page. Any thoughts on this theorem, though? So this segment version, now we're going to move on. This is basically the angle version of the same proof. You take any angle, and you take, yeah, so you flip it over. Any point on the angle bisector is equidistant from the side of the thing. It is the same except for angles. By the way, I took these numbers out, so these don't have names. What else did I say about this one? Okay, so over here is an example. This is an angle bisector because these are each 38. Therefore, these angles are congruent, so it's bisected the angle. Choose any point on the angle bisector, like that one, and the distance to the sides of the angle are the same. Again, it's because it's bisected, it's right in the middle. Let's see. And do you notice it has to be a perpendicular distance to the sides? The converse is also true. So if you're like, well, is this an angle bisector? Well, if you choose this point, and there to there, they're both 5, then yes, that would be an angle bisector. All right, we're going to prove this one right below here. If this diagram looks familiar, it's because it was number 6 from the cutout proofs activity. Again, you were just showing the triangles were congruent and that the segments were. You probably didn't know. You probably didn't know you were actually proving a theorem. Okay, so I'm going to write this all in. Perpendicular PR. Okay. So we have some given information, and we're going to prove these segments XZ and, well, XY and XZ are congruent. And to do so, I'm going to look at these two triangles here. And if I can get the triangles congruent, well, certainly the sides will be. That's what we do a lot in the future, guys. We say, oh, we can show the triangles are congruent, and then the angles or sides will be. So the goal is to get the triangle, it just becomes a triangle proof, show the triangles are congruent. Before we started on this one, I want to say this. You see all this given information up here? I want to remind you guys, I think I said this once before, but in your proofs, you're pretty much going to have to use all of it. So if you get to a spot and you're like, well, I didn't use this, you might want to go back and check your proof. Because there's a good chance you didn't do it right. You've got to use all of the given. For problems that I would give you. Okay, let's show the triangles are congruent. I'm going to start, I see that they share a side. Okay, so I'm going to do xp congruent xp. You also could have said px congruent px. That was one, it wasn't even in the given, but we can make that conclusion just from the diagram. Next one I'm going to do is this vocab word, bisect. Okay, now, it's very, very important. I think I stressed this before we even took the quiz yesterday. You have to make sure you know what it's bisecting. It'll tell you it's bisecting a segment or an angle. Right? It has to. So please just read carefully. It is bisecting an angle. It's not a segment bisecting. All right, so I'm going to draw that angle. So my angle bisector is right here. It says PX is bisecting QPR. Therefore, this angle there and that angle there are congruent. Right, bisected so that those little angles are congruent. I'll call it YPX and ZPX. There's other names for them, XPY and XPZ. Or even you could use QPX and RPX. And that's the vocab word. So, definition of angle bisector. That's good. We now have two parts. I marked my diagram, one pair of angles, one set of sides, shared side. We need one more thing. And you should say, I haven't used this given, so I'm going to use that. Perpendicular means forms right angles. Lines intersect to form right angles. So since xy is perpendicular to QP, this is a right angle. And we could do the other side, but it's not part of our triangle. And then xc is perpendicular to PR, so this is a right angle. And again, they mark the other one, but we only need the ones in the triangles. So remember, this is a two-step process if you see perpendicular. So you first are going to say perpendicular. Well, that means right angles. So I'm first just going to name them. Angle YPX and angle, what is, no, that's wrong. YPX. No, I'm sorry. PYX. PYX and PZX are right angles. That is simply what perpendicular means. So if it's what it means, it's vocab, we write definition of and perpendicular. All right, then the second step of this process that I said, then you say they're congruent. First you say that right angles are formed, then you say that angles you named are congruent. So angle PYX is congruent to angle PZX. Yeah.
Can you just say the triangles are congruent from here?
Yeah, that's going to be step 6.
Because you have the sides and then the angles.
Yep. And you did have to put these in, so even if you marked them as right angles, you have to state it here. They're right angles and then they're congruent. Okay. Yeah, you're right. The next step is the triangles are congruent. So all right angles are congruent. So that's why we could write that these angles were. They were right angles, so we say they're congruent. All right angles are congruent. And when Charlie said, now the triangles will be congruent. I look over here. That triangle, I have 2 angles and a side. In the bottom triangle, 2 angles and a side, and the side is not between the 2 angles. So it'll be NAS. Triangle, now I'm just going to use the same order here. PYX, congruent to triangle PZX. And that was still solving. AAS, angle on the other side. lots of times we'd be done, but now it says show the sides are congruent. So, what were they again? It was x, y, and x, C, P, C, T, C. Again, anytime at the end, if you're showing sides or angles, say the triangles are congruent, and then the last step will be the sides or angles are by C, P, C, T, C. All right, very good. I had one more little thing I wanted to finish up with, and then we'll work for 15 minutes. What kind of answer on that proof? Nothing? So notice this is a theme moving forward. You want to show a property is true? Well, many times, not always. Many times you're going to show the triangles are congruent. And then CP, CTC will help you get the end result. Last thing I want to show you at the bottom of this page is just about, this is actually something they cut from the standards. Well, I think it's just helpful to know. I'm not going to ask a direct question about this. I don't think the state will either. But it's just something good to know in trying how they work. Two little properties. I'll sum up each one. This one just says this. The wider your angle is, the longer the opposite side has to be. Right? The more smaller angle, it's not going to be much of a side over here. The bigger angle is going to have a longer side opposite it. And that's what this says. The bigger your angle, that corresponds with the largest side. It's the opposite side formed from that angle. If you have a small angle, like this one, then the opposite side is going to be the shortest side in that diagram. So the longest side of your triangle corresponds with the largest angle that's opposite. Smallest side of the triangle corresponds with the smallest angle. Hopefully that's one that just kind of makes sense. There's not going to be any direct questions on that. But who knows? Maybe if they give you something, this could help you eliminate an answer choice or something. And the last one has a name, triangle inequality theorem. It says that the sum of the lengths of any two sides in a triangle is greater than the length of the third side itself. So basically, if you have two sides here, so that side and this side, those two together are going to be longer than the third side. There's just no way that here, I could try and draw it like, say I make this segment a little flatter, and this one's going to keep approaching. If I end up making it perfectly straight, I can no longer draw in the third side. I'm trying to illustrate that like this plus this cannot be equal to that one. It would be a straight line. So what that means is that you take any two sides, you add them together, that length has to be longer than the third. So. All right, that pretty much sums it up. Segments in triangles and a few theorems about triangles.